Let Z5 equal to 0, 1, 2, 3, 4 be the set of residue class modulo 5. Show that Z5 is a group under the addition modulo 5, where the binary operation plus in Z5 is defined as the addition modulo 5. Thus, for a b belong to Z5, a plus b is equal to r, where r is the remainder obtained after division of a plus b by 5. Towards its solution, since Z5 has finite elements, so we will construct Cayley's table, and binary operation is of addition. So we will construct Cayley's table with respect to addition. Construct the Cayley's table. In top left corner, we will write the binary operation, that is addition in this case. And in first row and first column, we will write the elements of the given set, that are 0, 1, 2, 3 and 4. Similarly, 0, 1, 2, 3 and 4. The bar on the top of these numbers represents that they are residue classes. Now, by adding these elements one by one, we will write the elements of Cayley's table. Since it is given that modulo is 5, so after adding, if we get answer equal to or greater than 5, we will divide it with 5 and write the remainder as the answer. Firstly, let's add 0 with all these elements. 0 plus 0 is equal to 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. And 0 plus 4 is 4. Now we will add 1 with all these elements. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. And 1 plus 4 is 5. Since the number that we got after adding 1 and 4 is 5, that is greater than or equal. So now we will divide 5 with 5. 5 times 1 is 5 and we get remainder 0. So here we will write 0. Now we will add 2 with all these numbers. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5, which is equal to modulo. So we will divide 5 by 5. 1 times 5 is 5 and we get remainder 0. So we will write here 0. 2 plus 4 is 6, which is also greater than modulo, and when a number is equal to or greater than modulo, we divide that number by modulo. So we will divide 6 by 5. 5 times 1 is 5 and we get remainder 1. So here we will write 1. Now we will add 3 with all these numbers. 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is 5. Since 5 is equal to modulo, and when a number is greater than or equal to modulo, we divide that number by modulo. So we will divide 5 by 5. 5 times 1 is 5 and the remainder is 0. So here we will write the remainder, that is 0. 3 plus 3 is 6 and it is greater than modulo, so we will divide 6 by modulo, that is 5. 5 times 1 is 5, remainder is 1, so here we will write the remainder, that is 1. Now we will add 3 and 4, that is equal to 7. Since 7 is greater than modulo 5, so we will divide 7 by 5. 5 times 1 is 5, remainder is 2, so here we will write the remainder, that is 2. Now we will add 4 with all these numbers one by one. 4 plus 0 is 4. 4 plus 1 is 5, which is equal to modulo 5. So we will divide 5 by 5. 1 times 5 is 5. Remainder is 0. So here we will write the remainder, that is 0. 4 plus 2 is 6. 6 is greater than modulo 5. So we will divide 6 by 5. 5 times 1 is 5. Remainder is 1. So here we will write the remainder, that is 1. 4 plus 3 is 7. And 7 is greater than modulo 5. So we will divide 7 by 5. 1 times 5 is 5. And the remainder is 2. So here we will write the remainder, that is 2. 4 plus 4 is 8 and 8 is greater than modulo 5. So we will divide 8 by 5. 5 times 1 is 5. Remainder is 3. So here we will write the remainder, 3. Since we have constructed the K-list table, so now we will check the axioms of the group one by one. First axiom is closure law. Since all the answers in the K-list table are in Z5, which implies that addition modulo 5 is closed over Z5, that is A plus B belong to Z5 for all A, B belong to Z5, which means that the closure law is satisfied, which means that first axiom of the group is proven. Second axiom of group is associative law. Since addition is associative in residue classes modulo, so addition modulo 5 is associative over Z5, which means that A plus B plus C is equal to A plus B plus C for all A, B, C belong to Z5, which means that associative law is also satisfied. So second axiom of group is also proven. Third axiom is the existence of identity element. We know that 0 is identity with respect to addition. As 0 belongs to Z5, so 0 is identity with respect to addition modulo 5. Since the existence of identity element has also been proven, which means that the third axiom of group has also been satisfied. Fourth axiom is the existence of inverse. When we apply binary operation on two elements of a set and get identity, then those two elements are inverses of each other. Here the identity element is 0. So when we add 0 and 0, we get identity element 0, which means that inverse of 0 is 0. When we add 1 with 4, we get the identity element 0, which means that the inverse of 1 is 4. When we add 2 with 3, we get the identity element 0. So it means that inverse of 2 is 3. When we add 3 with 2, we get the identity element 0, which means that inverse of 3 is 2. When we add 4 with 1, we get the identity element 0, which means that the inverse of 4 is 1, which implies that inverse of each element of Z5 exists, which means that the fourth axiom of group is also satisfied. Since all the four axioms of group are satisfied, so we can say that Z5 under the binary operation addition is a group, which is required proof.